Welcome to The Sleepy Scientist. It is lovely to have you here. Before we begin, I would love to know where in the world you're watching from tonight. Are you settling into a quiet bedroom as the day finally softens? Listening on a sleepy train ride while the world drifts by in gentle blurs? Or perhaps resting on a cozy couch with a warm cup of tea close at hand? Wherever you might be, I hope you are comfortable, safe, and ready to drift slowly into thought. If you enjoy these relaxing explorations and would like to hear more, a like and subscribe truly helps this sleepy little channel float along, and to those already subscribed, thank you sincerely. Your support means more than you know. If you would like to catch each new upload the moment it appears, feel free to tap the notifications bell so nothing quietly slips past in the night. Now, I will try my best not to make tonight's topic too interesting, but if it does keep you awake a little longer than planned, at least you will drift off knowing something new about the tiny flashes of light that fill your world, a small, perhaps acceptable price for a restless night of gently glowing curiosity. So let us begin, shall we? What exactly is a photon? And how can something so familiar be so mysterious? The world you move through each day feels solid, dependable. You turn on a lamp, and light spills outward without hesitation. Sunlight warms your skin. Colours glide across your eyes from screens, reflections, and the sky overhead. Light feels simple, so ordinary that you almost forget it is there. But when scientists in the early 20th century began to look more closely, the nature of light stopped behaving politely. It rippled like a wave and arrived like a particle. It stretched across space and yet landed in one place at a time. It carried energy yet refused to possess any mass. Even stranger, it seemed to be created from nothing inside atoms, travelling endlessly until the moment it touched something and vanished in an instant. This was not an illusion or a trick of instruments. It was real, it was repeatable, and it transformed the way we think about the universe. A photon, it turned out, was not a tiny object with parts or pieces. It was a disturbance in a field, a brief gleam of energy, something so simple and fundamental that it could not be broken down into anything smaller. And the more scientists uncovered about these tiny packets of light, the more reality itself began to look softer, blurrier, stranger, and somehow more beautiful. So settle in, let your thoughts slow, and allow the quiet mystery of light to unfold. If photons are not made of anything at all, then what are they? Light touches your life so constantly that you almost stop noticing it. It glows softly through curtains in the morning, slips across your skin with warmth on gentle afternoons, and scatters in delicate patterns across walls, leaves, oceans, and clouds. It is there when you read a book, when you watch a screen, when you see someone smile, and when sunlight paints the world in colours that your eyes quietly translate into meaning. Every moment of sight, every sense of warmth, every breath of air sustained by photosynthesis depends on the steady arrival of photons. In a world full of complex mechanisms and intricate chains of cause and effect, it is astonishing how many of those chains begin with something so small and weightless that it barely seems to exist at all. When you think of the things that support life, you might imagine water, air, soil, or perhaps the food growing in fields and forests. But long before any of those existed in their present form, Earth was shaped by an unbroken stream of light arriving from the sun. Almost every living thing depends on tiny bursts of energy carried across space by photons. Plants cradle them within delicate leaves, turning each tiny packet into fuel for growth. Algae floating in oceans catch them and begin vast chains of life beneath the surface. Even you, whether you think about it or not, rely on photons constantly. Without them, there would be no warmth, no colour, no vision, no rhythm separating day from night. Life would not simply be different, it would be impossible. And yet, despite the familiarity of light, photons do not behave like anything else you encounter. They do not have mass in the way a pebble or a raindrop has mass. They do not slow down or settle. They have no interior, no layers, no structure in the traditional sense. A photon is not made from any smaller ingredient. It is a single, indivisible unit, something so simple that it cannot be broken apart, but so strange that it refuses to fit neatly into your everyday sense of how the world works. It is tempting to imagine a photon as a tiny bead flying through space, but that picture falls apart the moment you look closely. A bead has size and shape. It has edges. It has an inside and an outside. A photon has none of those things. It is described instead as a small, discrete packet of energy travelling within the electromagnetic field that fills all of space. This means a photon is not a little object racing from one point to another. It is a momentary excitation, a tiny disturbance moving through a field that is already everywhere. If the universe were a calm pond, a photon would be less like a pebble and more like a single ripple gently expanding outward, carrying energy without ever possessing substance. And it is remarkable how effortlessly that ripple travels. A photon leaving the sun glides across nearly 100 million miles of space without slowing, without tiring, without losing its identity. When it finally reaches Earth, it may be absorbed by a blade of grass, where its energy helps create the sugars that feed half the food chain. Another may strike your skin, warming it just enough to remind you that the world is alive and bright. Another might enter your eye and trigger a chain of events so sensitive that a single photon can be enough for your brain to register a tiny flicker of light. The more you focus on what photons actually are, the stranger they seem. They behave like waves when they spread out through space, yet they arrive in discrete all-or-nothing units when absorbed. They carry energy despite having no mass. They move at the fastest possible speed in the universe without any need for acceleration. They never slow down, never pause, never drift. They simply journey from where they are created to wherever they are absorbed, existing in a kind of pure motion. If they ever stopped, even for a moment, they would disappear entirely. And yet, despite all this strangeness, photons are woven into the most ordinary parts of life. Every colour you see begins with photons of different energies arriving at your eyes. Every warm patch of sunlight is made of photons striking your skin. When you sit by a fire and watch the flames dance, the flicker you see is nothing more than countless photons rushing outward. Even the deep blue of the sky is shaped by photons scattering in the atmosphere. At night, when you look up at distant stars, the faint light reaching you has travelled for years, sometimes hundreds, thousands, or even millions of years, to find you. During all that time, each photon remained whole, never dividing, never fading, never becoming anything else. It is a gentle reminder that light carries stories from places impossibly far away. A photon arriving from a distant galaxy may have begun its journey long before humans existed. It may have drifted through empty space for longer than recorded history. And yet, it reaches you in a fraction of a second once it meets your eye. It is poetic, in a quiet, cosmic way, that something so small and intangible can cross such impossible distances simply by being itself. When you begin to think of light not as a beam or a glow, but as a stream of tiny, fundamental quanta, it becomes easier to appreciate how delicate and extraordinary the world truly is. Life depends not on heavy machinery, but on the gentle dance of energy between atoms. Plants build themselves by catching photons. Animals see by absorbing them. Warmth is carried by them. Colour is sculpted by them. The flow of light is the heartbeat of the planet, even though it often goes unnoticed. And all of it comes from something that is not built from anything else. A photon has no parts to rearrange, no internal machinery to inspect, no hidden structure waiting to be uncovered. It simply exists, behaving in ways that feel both beautifully simple and endlessly puzzling. Familiar enough to brighten your living room, strange enough to challenge your deepest assumptions about reality. As you settle into the story of light, you may find it comforting to know that the universe relies on something so quietly elegant. A world built from light is a world built on the movement of energy across space, carried by particles that weigh nothing, occupy no fixed shape, and yet manage to sustain every leaf, every eye, every warm breath of wind. Light feels gentle because it is gentle, but beneath that calmness lies one of nature's most profound mysteries: how life can depend so utterly on something that has no mass, no structure, and no substance in the ordinary sense. And that mystery, slowly unfolding, is where the journey into photons truly begins. When you look at the world around you, almost everything you can touch or see is built from smaller pieces. A wooden table is made from planks, which come from fibres, which are made from cells, which are built from molecules. Even something as small as a grain of sand is a collection of countless atoms joined together. You are surrounded by things with layers and structure, each one assembled from parts that can be separated, taken apart, or rearranged. It is natural to assume that everything in nature works this way, that every object can be reduced to something smaller and simpler if you look closely enough. For a long time, scientists assumed the same. A stone could be crushed into dust, a drop of water could be boiled into vapour, a metal bar could be melted and reformed. Matter, it seemed, was made of parts all the way down. But as the study of atoms advanced, that comforting assumption began to fracture. Some things, it turned out, were not made from smaller pieces. They were not composed of building blocks. They simply existed as the basic ingredients of the universe, as fundamental as anything could be. The first surprises came from inside the atom. Protons and neutrons, once thought to be the tiniest indivisible components of matter, were discovered to have internal structure. They contained even smaller particles called quarks, bound together by the strong nuclear force. Electrons, on the other hand, had no such structure. They were truly elementary. No matter how hard researchers tried, no experiment ever revealed a smaller piece inside an electron. There was nothing to break apart, nothing to open, nothing to divide, and photons, the tiny packets of light that play such a central role in your life, belong to this same category. When something has no parts, it behaves differently from the objects you encounter every day. Think of a soap bubble floating through the air. It looks smooth and simple, but even the bubble is made from a thin layer of molecules arranged in a delicate film. If you could zoom in far enough, you would see the molecules that form its structure. A photon has no such underlying complexity. There are no molecules, no atoms, no particles inside it. There is no interior at all. It is not a shell filled with anything. It is not a cluster of components arranged in a pattern. It is a single, indivisible unit, as pure as a concept and as simple as nature can make something. This kind of simplicity is surprisingly difficult to grasp, because the human mind is trained by experience to imagine things that have parts. Even a raindrop, which seems smooth and featureless, is made from countless water molecules joined together by electrical attraction. Even the air around you is a mix of different molecules, each one built from atoms, each atom containing protons, neutrons, and electrons, each of those built from even smaller particles and fields. The idea of something with absolutely no internal structure, nothing to uncover, no hidden layers at all, feels almost unnatural. But a photon has no hidden layers. It has no weight to anchor it, no surface to define it, and no internal machinery to explain. It is not a miniature object travelling through space. Instead, it exists as a small excitation or ripple in the electromagnetic field, carrying energy from place to place without needing anything inside it to support that motion. If it had parts, those parts would need to be arranged, held together, and given some kind of structure. But a photon is a fundamental entity. It simply exists as it is, without assembly, without internal scaffolding, without anything smaller waiting to be discovered. This purity gives photons a kind of elegance that can be difficult to articulate. Most objects can be taken apart and studied piece by piece. Even a proton, which seems incredibly small, can be understood in terms of its quarks and the forces that hold them together. But with a photon there is no inside to explore. The photon is complete in a single step. When it is created, it comes into existence as a whole. When it is absorbed, it disappears as a whole. There are no fragments left behind, no leftover components. It is as if a small amount of energy briefly forms a self-contained promise of motion, carries that promise across space, and then quietly hands it over when the journey ends. This lack of structure does not make photons boring. It makes them extraordinary. Because they have no parts, they cannot rest. A particle with mass can sit still. It can sleep on a table or hover in place. A photon cannot. If it ever stopped moving, even for a single moment, it would no longer exist. Something that has no mass and no internal structure only survives by travelling. It is created in motion, and continues in motion until something absorbs it and brings its journey to an end. It is a little like a ripple on a lake that can only exist while it moves outward. The moment it stops, it vanishes into stillness. When scientists talk about elementary particles, they are referring to these indivisible building blocks of the universe. They are the pieces from which everything else is made. Some of them, like quarks, combine to form other particles. Some, like electrons, exist as simple, unbroken units that form the outer structure of atoms. And some, like photons, carry forces and energy across space without having size or shape. They sit at the foundation of reality, forming the bedrock upon which everything else is built. The idea that a photon has no parts is not a poetic description. It is a physical truth confirmed by countless experiments. No collision, no scattering, no measurement has ever revealed anything smaller hiding inside a photon. It behaves exactly as something without internal structure should behave. It cannot be split. It cannot be opened. It cannot be peeled apart like an onion or cracked like a shell. It is a solitary quantum of the electromagnetic field, complete from the moment of its creation to the moment of its disappearance. As you think about this, the simplicity of a photon begins to feel strangely beautiful. In a world full of complex structures and layered systems, it is delightful to realize that some of the most important things, light, warmth, color, the energy that makes life possible, are carried by something so fundamentally simple. There is no machinery hidden inside. There is no puzzle waiting to be solved. The photon is exactly what it appears to be, a tiny burst of energy travelling through the universe with perfect clarity. When you look at it that way, the idea of an object with no parts becomes less confusing and more elegant. It is a reminder that nature does not always build things from smaller pieces. Sometimes it begins with the most simple ingredients imaginable, and from those pure, indivisible building blocks, it constructs the staggering complexity of the universe. In that sense, the photon stands as one of the most impressive achievements of nature's simplicity, a particle that is nothing more than itself, yet powerful enough to illuminate entire worlds. If you close your eyes for a moment and imagine the space around you, you might picture emptiness. A still volume of air perhaps, or the quiet dark of a room at night. It is easy to believe that once you remove objects, once you take away the furniture, the walls, the dust, the air itself, what remains is nothing at all. But this sense of emptiness is an illusion. Even in the deepest stretches of space, far beyond planets, stars and drifting clouds of gas, the universe is not built from a hollow void. It is built from something quieter, something more subtle, something that does not depend on objects or boundaries to exist. It is built from fields. Fields are not things you can touch, and they do not collect in piles or drift like mist. Instead, they exist everywhere, all the time, forming an invisible foundation beneath everything else. A field is a presence, a condition, a subtle backdrop that permeates all of space. If you imagine the universe as a vast, calm ocean, the fields would be the water itself, ever present, supporting every ripple and every wave that forms within it. Even when no ripples are visible, the ocean remains. In the same way, a field remains, even when nothing appears to be happening. One of these fields is the electromagnetic field, a quiet and continuous expanse that surrounds you completely. Whether you're walking through the sunlight, sitting beneath the gentle glow of a lamp, or floating in the dark between the stars in your imagination, the electromagnetic field is always there. It never switches off. It never flickers or dims. It simply exists, filling the universe with potential. It is within this field that photons appear, travel, and disappear again, carrying energy from place to place with remarkable ease. When you hear the word field, you might think of a grassy meadow stretching out beneath a wide sky. In a way, that image is not so far from the truth. A real meadow stretches out quietly, its stillness broken only when wind moves through the blades of grass. The electromagnetic field stretches out across the universe in a similarly peaceful way. Most of the time, it lies in a calm, unbroken state. But when energy moves through it, when something disturbs this quiet backdrop, ripples begin to form, tiny, delicate tremors of activity. A photon is one of those ripples. To understand this more clearly, imagine resting your hand on the surface of a serene lake at dawn. The water feels still and smooth beneath your fingers. Then, with a small movement, you create a gentle wave. That wave glides outward, carrying energy but carrying nothing inside it. It looks simple, but it is not made of smaller pieces that travel with it. It is a momentary pattern in the water. When the wave passes, the water returns to its original calm. A photon behaves in a similar way. It is not a tiny object travelling through the electromagnetic field. It is a temporary pattern of energy in the field itself. It is a ripple, a trembling note, a brief shimmer that moves through space without needing a physical body to support it. And just like the wave on the lake, a photon vanishes once its energy has been absorbed. The field returns to its quiet state, the disturbance fades, and nothing material remains. This idea, that photons arise from changes in the electromagnetic field, is one of the most important concepts in modern physics, yet it can be explained in a gentle, intuitive way. When an atom in a star, a lamp filament, or a firefly becomes excited and then settles back into a more restful state, it releases a small amount of energy. That energy does not drift away as a tiny glowing bead. Instead, it becomes a ripple in the field. The ripple spreads outward, moving at the cosmic speed of light, carrying with it the exact amount of energy that the atom released. That ripple is the photon. Because of this, photons do not need an interior. They do not need parts or pieces. They arise purely from the behavior of the field itself. When the field changes, photons appear and move away. When the change ends, they disappear. Their existence is tied so closely to the field that thinking of them as separate objects can sometimes feel misleading. They are events just as much as they are particles, brief but beautifully ordered disturbances that carry information across the vastness of space. Fields have a way of hiding in plain sight. When you switch on a lamp and watch the room fill with light, you are seeing the electromagnetic field in action. When sunlight warms your skin, the field is delivering energy from the sun to your body through the gentle arrival of countless ripples. When you listen to the hum of a radio or feel the subtle pull of a magnet, you are sensing the behavior of the field in different forms. You live your entire life within fields, yet you almost never notice them. They're quiet, patient, and always present. It can feel strange to imagine that everything around you depends on invisible structures that extend through space. But fields are not abstract mathematical tricks. They are the actual fabric of reality. Every particle, every force, every interaction is shaped by them. Even emptiness is built from fields. If you could somehow remove every particle of matter from a region of space, the fields would still be there, stretching out in calm silence, waiting for the next disturbance. The electromagnetic field is only one of several fields that fill the universe, but it is the one you encounter most directly. It gives rise to photons. It shapes electricity and magnetism. It sculpts the colours you see, and it carries energy from the depths of stars to the surface of your eyes. It is one of the quietest and most reliable companions you will ever have, and it is working all around you, all the time, whether you notice it or not. Thinking of fields in this way, soft, continuous, ever-present, can make the universe feel more peaceful. Instead of imagining space as a cold emptiness dotted with occasional stars, you begin to sense it as a living, dynamic environment filled with gentle background structure. It becomes easier to picture photons not as tiny objects racing around, but as graceful ripples moving through a cosmic ocean. Their beauty lies not in their shape, but in the simplicity of their motion. Once you begin to appreciate fields for what they are, the behavior of photons becomes far less mysterious. They do not need parts because they are patterns. They do not need weight because they are excitations of something that is already everywhere. They do not need rest because a ripple cannot stop without disappearing. Everything about them makes sense when you imagine them as gentle tremors in the electromagnetic field, born from energy and extinguished when that energy is delivered. Perhaps the most astonishing part of this idea is its quietness. Fields do not make noise. They do not glow or shimmer unless disturbed. They simply exist, filling the universe with possibility. Photons are the graceful movements within that stillness. They carry warmth, colour, and information across unimaginable distances, tracing pathways through a world that is constantly shaped by fields you cannot see but rely on completely. When you understand this, light becomes something more than a glow or a beam. It becomes a conversation between energy and the hidden fabric of reality. A photon is not just a particle of light. It is the universe briefly stirring, sending a ripple through space and allowing you to see, to feel warmth, to live. In that sense, the electromagnetic field is not just a backdrop. It is the quiet stage on which the drama of light unfolds, holding every ripple with gentle precision and letting each photon drift freely until its journey comes to an end. When you hear the word pulse, it is easy to imagine something solid, a tiny bead of light perhaps, or a miniature glowing pebble racing through the darkness. But a photon is not a solid object pushing its way through space. It does not have edges or a surface. It does not carry a shell or a core. Instead, a photon is better imagined as a tiny pulse in the electromagnetic field, a brief and delicate disturbance that moves forward with remarkable grace. If you picture the electromagnetic field as an unimaginably wide ocean, calm and still across infinite space, then a photon would be one of the smallest ripples that ocean can hold. Not a crest rising high above the surface, but something much subtler, a faint tremor, a momentary shiver that travels outward without ever breaking, without ever needing a physical form to carry it. It exists because the field exists, and it moves because the field allows it to move. The photon is the ripple, not a stone tossed into the water. This kind of motion is surprisingly difficult to compare to everyday experiences, because most of the things you see around you are made of matter. Even the smallest dust particle is still an object with size, weight, and an interior. It can be held, moved, stopped, or bounced. A photon cannot be caught or halted in that way. If it stops, it ceases to exist. It survives only through travel, only through motion, only as a pattern that continues to unfold. To make the picture clearer, imagine someone creating a gentle vibration on one end of a long stretched rope. The wave travels down the length of the rope, carrying energy from one place to another, but the rope itself does not move with the wave. Each little segment simply lifts and settles as the wave passes through. The energy is carried forward, even though the rope stays in place. A photon works in a similar way, except that there is no rope, no string, no physical structure that you can point to. The electromagnetic field plays the role of the rope, and the photon is the wave. That idea can be comforting once you let it settle. A photon is not a mysterious object appearing out of nowhere. It is the natural movement of a field that fills all of space. When an atom releases energy, the field reacts gently, forming a pulse that begins to move away. It is a bit like tapping the surface of a drum with the lightest possible touch. The drumhead vibrates gently, sending a soft wave outward. But unlike a drum, the electromagnetic field is everywhere, and the wave travels not through material but through the very structure of space. People often compare light to sound, and while the comparison is helpful, it also reveals something important about how photons differ from the waves you hear. Sound requires a medium. It needs air, water, or a solid surface to travel through. When a sound wave moves, it is really the air molecules bumping into one another, passing energy along in a chain reaction. If you remove the air, the sound has nothing to move through, and silence spreads instantly. Light is not like that. A photon does not need air, water, or any material substance. It travels through empty space, just as easily as it moves through the air in your room. That alone tells you that it is not made of matter and does not rely on matter to exist. Instead, it travels through the electromagnetic field, which is already present even if nothing else is. This makes a photon feel almost weightless, in a deeper sense than simply having no mass. It is a pattern riding on something that is everywhere, something you cannot see, and something that never disappears. The movement of a photon is gentle but profoundly steady. It does not speed up or slow down. It does not drift or wobble. It flows at a constant and universal pace, always moving at the cosmic speed limit built into the geometry of the universe. This speed does not come from the photon pushing itself or propelling forward. It comes from the nature of the field itself. The field guides the ripple along, carrying it with complete reliability, never altering its pace. It is as if the universe offers one specific speed at which energy can move through the electromagnetic field, and the photon simply follows that rule without hesitation. Even though its structure is not that of a solid object, a photon still carries information. It can carry colour, which is linked to the energy of its ripple. It can carry direction, showing where it came from. It can carry the story of its birth, whether that birth was inside a star, a glowing ember, or an atom excited by an electric current. Everything it carries is contained not in an object, but in the behaviour of the wave itself. It becomes a travelling signature, a whisper from one point in the universe to another. If you think again of the calm ocean, you might imagine that the smallest ripple has no meaning, but even a faint tremor can tell you something. It can reveal where the disturbance began, how strong it was, and what direction it is heading. In the same way, a photon contains just enough information to let you know how it was created and how much energy it brings. Its simplicity does not limit it. It defines it. The pulse remains whole throughout its journey, never breaking into pieces, never losing its identity, no matter how far it travels. When the photon encounters something that can absorb its energy, the ripple ends. The disturbance fades. The energy is passed along, perhaps warming your skin, perhaps triggering a chemical reaction in a leaf, perhaps creating a tiny electrical signal in your eye. In that moment, the photon itself vanishes completely. There is no leftover fragment, no cooling ember, no dying spark. The ripple stops, the field becomes calm again, and the photon story concludes. It is a peaceful thought in a way. A photon begins as a disturbance, spends its life travelling gracefully through space, and ends by giving all of its energy to something else. The entire journey is one fluid motion. Nothing is wasted, nothing breaks, and nothing lingers. It arrives, it travels, and it disappears. If it could be aware of itself, it might not even think of this as an ending. It might see its story as complete the moment its energy finds a new home. Understanding a photon as a tiny pulse of the electromagnetic field turns light into something more than a beam or a ray. It becomes a delicate rhythm, a quiet shiver that the universe sends through its own fabric. It becomes a reminder that not everything that moves needs a physical body, and not everything that carries energy needs weight. The most fundamental messengers of the universe travel not as objects but as patterns, beautifully simple and endlessly subtle. And perhaps the most soothing part of this idea is how natural it becomes once you picture it clearly. A photon is not a glowing dot racing through the darkness. It is a gentle unfolding in a field that fills all of space, a momentary tremor carrying warmth and colour through a quiet, invisible ocean. It is movement made pure, energy made elegant, and light expressed in its simplest form. Mass is one of those ideas that feels simple until you try to explain it. You pick up a stone and it feels heavy. You lift a feather and it feels light. You push a shopping cart and feel resistance. You push a wall and feel even more. In everyday life, mass shows up as weight, as effort, as a kind of reluctance objects have when you try to change what they are doing. Something with mass resists being moved if it is resting, and resists being stopped if it is already moving. It carries inertia, the quiet tendency to continue its current state unless something nudges it in a different direction. When you walk, every step is a conversation with mass. Your body pushes forward against the ground and the ground pushes back, allowing you to move. If you were weightless, the smallest push would send you drifting away like a balloon, unable to stop yourself easily. Mass anchors you. It gives you presence, solidity, and a sense of stability in the world. Now imagine something that has none of that. Something so light that it does not just feel easy to move. It cannot ever be at rest. It cannot sit still on a table. It cannot float lazily in a corner. It cannot slow down or pause for even a moment. That is what it means for a photon to have no mass. It is not just weightless in the everyday sense. It is free of the very property that ties objects to the rhythms of motion and stillness. To picture this, imagine trying to hold a ripple in your hand. You cannot. The moment you try to bring it close, it moves away. A ripple on water exists only through motion. The instant it stops travelling, it vanishes back into the stillness of the lake. A photon behaves in much the same way. It is a small pulse of energy in the electromagnetic field, and its existence is tied completely to movement. If it were to stop even briefly, it would no longer be a photon at all. It would simply cease to exist. Mass gives objects the ability to rest. Remove mass and the concept of resting disappears. A photon is born in motion and continues in motion until its journey ends, carrying energy from one place to another. It never needs to accelerate, because acceleration is something that applies to particles with mass. A photon begins its life already travelling at the fastest speed the universe allows, as if the cosmos itself whispers, "Go," and the photon obeys instantly and forever. This speed, the cosmic speed limit woven into the fabric of spacetime, is not arbitrary. It is the speed at which ripples in the electromagnetic field naturally move. If you imagine dropping a pebble into a pond, the ripples glide outward at a speed determined by the properties of the water. They do not hesitate or negotiate. They simply follow the rules of the pond. The photon behaves the same way, travelling at a fixed pace set by the nature of the field it inhabits. It is almost poetic that a particle with no mass travels not just quickly, but at the absolute maximum speed any information or energy can achieve. Nothing slows it down, because nothing about it interacts with the world in a way that creates resistance. It does not collide with air molecules in the way a pebble would. It does not experience friction. It does not press against anything. It glides effortlessly, not because it is powerful, but because it is simple in a way that matter can never be. Consider the difference between pushing a heavy box across the floor and sliding a single sheet of paper through the air. The box grips the ground, resists movement, and needs constant effort to budge. The paper floats freely, carried by the slightest breeze. Now imagine something even lighter than the paper, something so light that the concept of pushing no longer applies. This is the world a photon lives in, a world without weight, without friction, without the pull of inertia. Its movement is closer to the effortless drift of light reflections on water than to the motion of any solid object. If you have ever watched a beam of sunlight filter through dust particles in a quiet room, you can almost sense the contrast. The dust particles fall slowly, pulled by gravity, their paths influenced by every small current of air. But the light streaking between them does not fall. It does not drift sideways. It does not hesitate. It travels in straight lines, untouched by the currents that disturb everything else. The dust lives in a world of mass. The light lives in a world beyond it. The idea that something can have no mass might feel abstract, but the consequences are simple and profound. It means a photon cannot resist motion, because resistance requires mass. It cannot accumulate inertia, because inertia is mass. It cannot ever be at rest, because rest is only meaningful for objects that can choose between stillness and movement. The photon is always moving because its very nature depends on movement. If you picture a leaf falling through the air, you see mass at work. The leaf drifts, turns, slows, and eventually touches the ground, carried by the push and pull of forces. A photon, by contrast, is like a leaf made entirely of motion. It does not fall, it does not drift, it does not settle, it exists as pure travel. Not because it is trying to reach a destination, but because travel is the only state in which it can exist at all. This constant motion is also why photons can cross such vast distances without losing their identity. A photon from a distant star may travel for thousands or millions of years before reaching your eye. During that entire journey, it does not slow or fade. Its lack of mass allows it to maintain a perfect, unwavering pace through the emptiness of space. Every moment of its existence is motion, and every moment of that motion is identical to the last. There is something wonderfully serene about this. A photon begins as a quiet disturbance, travels across the cosmos without effort, and ends by giving all of its energy to whatever absorbs it. It is a life lived entirely in transition, entirely in motion, without any of the complications that come from having mass. It does not struggle or strain. It simply moves. Understanding why photons have no mass turns them from mysterious entities into elegant ones. Their freedom from mass is not a flaw or a limitation. It is the very thing that allows them to carry the warmth of the sun across space, to illuminate your world and to reveal the colours and shapes that fill your life. Their masslessness is not emptiness, it is possibility. It is the quiet grace of energy moving as simply and beautifully as nature allows. If you watch cars on a road or birds crossing the sky, you notice something simple about motion. Different things move at different speeds. A car accelerates from a stop, gathering pace little by little. A bird might take off slowly, flap harder, and then glide. Even water flowing down a river can speed up or slow down when the terrain changes. In everyday life, nothing moves at a fixed, unchanging pace. Everything that has mass must work for its motion, and the speed it reaches depends on how much force it receives and how much resistance it encounters. Light does not behave this way. A photon does not begin slowly and pick up speed. It does not push against anything. It does not build momentum. It does not accelerate the way a thrown ball or a falling leaf does. Instead, a photon comes into existence already moving at the fastest speed the universe permits. It is created in motion and stays in motion for as long as it exists, without ever slowing down, without ever changing pace. This strange behavior is not caused by the photon itself. It is a property of the universe. The structure of spacetime, this quiet, invisible fabric that shapes the rhythm of distances and durations, sets the speed at which ripples in the electromagnetic field can travel. That speed is not decided by the photon. It is built into reality. One gentle way to imagine this is to picture the universe as a vast calm ocean once again. The surface of that ocean has a natural speed at which ripples can move. You cannot persuade a wave to travel faster than the water allows. You cannot shout at it or push it or plead with it. The wave simply moves at the inherent speed defined by the water's properties. In the same way, a photon travels at the speed set by spacetime itself. This cosmic speed limit is woven into the very geometry of the universe, the same geometry that tells clocks how to tick and rulers how to measure distance. When a photon is released, whether from an excited atom, a distant star, or a spark in a firefly, it appears in the electromagnetic field, already travelling through space-time at this fixed pace. No warm-up, no acceleration, no hesitation, just immediate, perfect motion. Because photons have no mass, nothing slows them. They feel no inertia. There's no weight to anchor them, or friction to diminish their journey. They skim across the universe with astonishing consistency, following the contours of space-time like a dancer following the shape of a melody. Even when gravity bends their paths, it does not reduce their speed. It simply guides them along a curved trajectory. To make this idea even more intuitive, picture walking on a moving walkway at an airport. No matter how lightly you stroll, the walkway carries you forward at its own steady pace. You can choose to walk faster or slower relative to the walkway, but you cannot change the speed at which the walkway itself moves. A photon has no option to stroll or sprint. It is carried completely by the movement allowed within space-time. It does not choose its speed any more than a ripple chooses the speed at which it spreads across a lake. This has a curious consequence. To a photon, time behaves differently than it does for you. Photons do not age. They do not experience the passing of seconds or the slow accumulation of moments. From their perspective, if such a perspective could exist, their entire journey begins and ends instantaneously, whether they are travelling across the width of a room or across a galaxy over millions of years. They are creatures of pure motion, and motion at this extreme pace reshapes the meaning of time itself. Einstein's theories of relativity help explain this phenomenon, though we can explore it without diving into heavy mathematics. In relativity, time and space are linked. When something with mass accelerates, it uses energy both to increase its speed and to reshape how time flows for that object. The closer it gets to the cosmic speed limit, the more difficult it becomes to accelerate. It is like trying to run through deep water. The harder you push, the stronger the resistance feels. Objects with mass can get close to the speed of light, but never reach it, because doing so would require infinite energy. A photon faces none of this. Because it has no mass, it does not need to fight through any resistance. It does not need energy to accelerate. It has no inertia to overcome. So it simply exists at the one speed the universe allows for massless particles. This speed shapes so much of what you see and feel. When sunlight reaches your skin, it has travelled across nearly 100 million miles at this fixed pace. When you gaze at stars, the light entering your eyes has been travelling for years, decades, centuries or more. And yet, no matter how far it has come, the photon has never slowed. It has maintained the same speed every moment of its existence, running through space-time along a perfect, unbroken path. There is calm certainty in this behaviour. The universe is often unpredictable, but the speed of light is one of the rare constants that never wavers. It is the same in every place, at every time, for every observer. Whether you are moving toward the source of light or away from it, the photon still travels at that same cosmic pace. This stability becomes a kind of anchor for physics, a quiet rule that helps shape everything from the structure of atoms to the expansion of the universe. Think of space-time as a vast stage where many performances unfold at once. Some actors move slowly, some sprint, some drift lazily, or curve gently around unseen gravitational wells. But photons glide across the stage at a speed no one else can match, following the single tempo set by the universe itself. Their pace is not personal, it is structural, it is determined by the very stage beneath their feet. The fact that photons always travel at the speed of a light is not just a fascinating detail about how light behaves. It is part of the deep symphony of nature, one of the harmonies that keeps the universe coherent and connected. It ensures that warmth and colour can cross space, that information can travel from one point to another, that stars can shine across cosmic distances, and that your eyes can turn those tiny pulses of energy into images and meaning. It is difficult not to feel a sense of peace in that thought. Light is steady, light is reliable, light moves with the same unwavering pace through every corner of the universe, whether crossing the space between atoms or the emptiness between galaxies. Photons do not rush, they do not tire, they do not vary their speed in moments of stress or calm. They follow the rules of spacetime with quiet precision, carrying energy in the simplest, most elegant way possible. When you imagine a photon travelling across the universe, picture not a frantic race but a serene glide. Picture a ripple moving across the most tranquil sea imaginable, smooth, effortless, unchanging. That is how light moves. That is how photons exist. And that is why every sunrise, every starlit night, every flicker of a candle is made possible by a pace set not by the photon, but by the universe itself. If you imagine an atom as a tiny solar system, with a dense nucleus at the centre and electrons moving in delicate layered orbits around it, you're already most of the way toward understanding how photons come into being. The details are different from planets and moons, of course, but the broad idea helps. Electrons do not wander freely. They occupy specific energy levels, almost like steps on an invisible staircase. And those steps are precise. An electron cannot float somewhere between them in a casual mid-air pause. It must be on one step or another. Now electrons are restless creatures. They are constantly nudged by energy, from heat, from collisions, from electric currents, from the warmth of starlight drifting through space. When an electron absorbs just the right amount of energy, it can leap from one step to a higher one. Think of it as climbing a rung on a ladder. But this excited state never lasts long. The universe prefers stability, and electrons quietly agree. So after a short moment of excitement, the electron slips back down to a lower energy level. When it does, the extra energy it no longer needs does not simply vanish. Nature never throws away energy, it transforms it. And in this case, the transformation is simple and elegant. The atom releases the leftover energy into the electromagnetic field as a tiny pulse. That pulse is a photon. This moment is so small and so fast that it is difficult to picture, but you can imagine it as a quiet flick of light emerging from the atom's interior, a gentle shimmer slipping away into the surrounding space. It is not a spark in the fiery sense. It is more like a whisper of energy, leaving the atom with absolute precision. And because the atom releases a very specific amount of energy, a difference between the two steps of the invisible ladder, the photon carries exactly that amount, not more, not less. A photon is, in effect, the perfect envelope carrying the exact change from the electron's transition. This is why photons have different energies depending on how they are created. If an electron falls a large distance between energy levels, the photon it releases is more energetic. If the step is smaller, the photon is gentler. Your eyes detect these differences as colours. Photons with higher energy appear as blues or violets. Lower energy photons arrive as reds. Everything in between paints the world with the colours you see each day, but electron transitions are only one of the ways photons come into existence. Nature has a wonderfully generous habit of producing them in many situations. Whenever something is warm, even slightly warm, atoms inside it vibrate and jiggle. Those tiny motions cause electrons to move in subtle ways, releasing a steady stream of photons. This is why everything above absolute zero emits some amount of light, even if most of that light is in a wavelength you cannot see. A hot stove glows red. A piece of metal heated in a forge glows orange, then yellow, then white. Each glow is the language of photons, spoken through temperature. Starlight is another source, perhaps the most poetic one. Deep within a star's core, atoms are squeezed together so tightly that they fuse, releasing vast amounts of energy. That energy drifts outward, hopping from atom to atom in a process that can take thousands of years. Eventually it reaches the star's outer layers, where countless electrons shift, settle, and release photons that escape into space. Some of those photons travel across unimaginable distances and end their journey in your eyes. The soft twinkle of a star is not the star itself. It is a stream of ancient photons finally completing their long journey through spacetime. Chemical reactions also produce photons, including some you may have seen without realizing it. When something burns, for example, the rearrangement of atoms causes electrons to jump between energy levels, releasing photons as part of the process. Flames glow because electrons are busy leaping and settling, constantly sending out small packets of energy. Even the gentle spark from two flints striking each other is a flurry of photons being released from atoms jarred into excited states. And if you have ever watched a firefly in the summer, blinking softly in the evening air, you have watched a living organism orchestrate chemical reactions specifically to create photons. A firefly's glow is nature performing its own tiny symphony of transitions. One of the most charming things about photons is how quietly they begin. There is no violent kick, no dramatic explosion, no miniature trumpet announcing a new particle's arrival. A photon's birth is serene. It is a rearrangement of energy, a small difference being released with perfect accuracy, a delicate pulse slipping into the electromagnetic field as gracefully as a breath of air. You can imagine an electron releasing a photon the way a harp string releases a note. The string vibrates, the note escapes, and both settle into stillness afterward. The photon carries a tiny piece of the atom's energy outward, moving at the speed of light the instant it appears. There is no warming up, no gathering momentum, just an immediate transition from stillness to motion. And if you like a moment of gentle humour, you might imagine electrons as fidgety musicians who cannot resist plucking at their strings. Every time they settle down after absorbing energy, they send another shimmering note into the universe. The symphony never ends. Every star, every warm object, every living thing contributes its own tiny melody of photons. The universe is constantly glowing, singing in packets of light, even if your eyes can hear only the smallest part of that song. The most beautiful part is that these photons, born from such delicate changes, become the foundation of sight, warmth, and life. A single photon released deep within a star might travel for millions of years before brushing against your skin or slipping into your eye. A photon released by a leaf may help another plant recognize the presence of sunlight. A photon emitted by your phone screen may be the one that shows you a message from a friend. Each one is a tiny carrier of energy, a messenger without mass, a flicker of information that began with a simple rearrangement inside an atom. The creation of photons is not dramatic, it is not forceful, it is not violent, it is gentle, precise, and constant. Energy shifts, and light is born. A ripple begins in the electromagnetic field, and the photon's journey unfolds. By the time it reaches you, it may have crossed distances so enormous that the human mind struggles to imagine them, yet the photon itself remains unchanged from the moment of its creation. And so, every beam of light, every warm glow, every spark, every gleam in someone's eyes begins with a tiny rearrangement inside an atom. A small shift, a quiet release, a pulse of energy that slips into space, ready to travel the universe with perfect grace. Colour feels like one of the most familiar parts of everyday life. You open your eyes in the morning and the world greets you with soft blues, quiet greys, warm yellows, or whatever palette the sky has chosen for that particular moment. You pick up fruit and notice its ripeness through hints of green or red. You recognize friends by the colors of their clothes, their hair, their eyes. And yet, beneath all this comfort and familiarity, color is simply the story of photons carrying different amounts of energy. That is all. What feels like a sweeping canvas of hues and shades is really a spectrum of tiny pulses of light, each one arriving with its own distinct energy, its own soft signature. When an electron inside an atom settles into a lower energy level and releases a photon, the exact amount of energy it lets go determines what kind of photon appears. If the energy difference is large, the photon is more energetic. If the difference is small, the photon carries less energy. These small variations create the entire rainbow. Higher energy photons are seen as blues and violets. Lower energy photons arrive as reds and oranges. Everything in between glows with the colours you see woven throughout the world. This means that colour is not a coating on objects or a dye in the air. It is not something painted onto the surface of the world. Colour is a message. It is a whisper of energy carried by photons that your eyes translate into sensation. The blue of the sky is the result of photons scattered by air molecules. The deep red of a sunset comes from sunlight, passing through a thicker layer of atmosphere, where the lower energy colours slip through more easily. The green of a leaf emerges from photons that plants reflect after absorbing other colours to power their chemistry. What you call colour is really your brain's interpretation of light's energy, a quiet collaboration between physics and perception. To understand this gently, imagine holding a prism up to a beam of sunlight. The white light, which appears so plain at first, spreads into a fan of colours. Each colour bends slightly differently because each colour's photons carry a different amount of energy. The prism does nothing magical. It simply reveals what was always hidden within the light. Every ray of sunlight contains a spectrum, a blend of energies layered over one another, and your eyes are exquisitely tuned to interpret those energies. But while your eyes can detect colours beautifully, they do not see the full range of energies that photons can carry. Some photons have too little energy for you to notice. These are the gentle, comforting photons that warm your skin on a cool day. Others carry far more energy than your eyes can handle, slipping into the realms of ultraviolet and beyond. These high-energy photons can affect living cells, which is why sunlight both nurtures and challenges life. So the colours you see represent only a small portion of the full symphony of light. Your eyes hear a few notes, while the universe plays the entire score. This connection between energy and colour becomes even more beautiful when you look beyond Earth. Stars, for example, are natural factories of color. A star's temperature determines the energy of the photons it emits. Cooler stars glow in deep oranges and reds, like embers resting in the hearth of the cosmos. Hotter stars shine in brilliant whites and blues. When astronomers look at starlight through their instruments, they can read the rainbow of energies within it and learn a star's temperature, age, chemical composition, and even how fast it is moving. In that sense, starlight becomes a letter from across the universe written entirely in colour. Nebulae offer another kind of cosmic artwork. These vast clouds of gas and dust glow when they are illuminated by nearby stars. Hydrogen emits a soft, rosy red when excited. Oxygen glows in shades of cool teal or pale green. Sulfur radiates in gentle red tones. When photographed through special filters, nebulae appear like enormous swirling paintings suspended in space, each stroke defined by the photons escaping atoms light years apart. The colours do not come from pigments or dyes. They come from electrons jumping between energy levels and releasing photons with precisely defined energies. And yet, for all this scientific precision, colour feels emotional and intimate. A warm golden sunset can make you feel calm. A cool blue morning can bring a sense of clarity. A forest of green can soothe your mind. These feelings arise not just from the physical properties of photons, but from the way your brain has evolved to interpret their energy. Humans have built entire languages around colour, symbolism, art, expression. Yet at the heart of it all lies a simple fact. Colour is energy, arriving in tiny packets, transformed by your mind into meaning. In a way, colour is where physics and emotion meet. A photon does not carry a preference for beauty. It does not know that it will paint the sky or give life to a field of flowers. It simply travels, carrying energy across space. But when that energy meets your eyes, it becomes something more. It becomes perception. It becomes mood. It becomes memory. The same photon might warm your skin, grow a plant, or reveal the shades of a rainbow. It is astonishing how much can come from something so small. Perhaps one of the most calming thoughts is that the colours you see every day are part of a larger cosmic palette. The soft blue glow of Earth's atmosphere, the warm gold of the sun, the deep reds of distant stars, the ghostly purples of nebulae, each one is written in energy. When you look up at the night sky, you are seeing photons that began their journey long before you were born, carrying their colours across unimaginable distances. Some may have been created in events older than human history, drifting patiently through the darkness until they reach your eyes. Colour becomes a gentle reminder of how connected you are to the universe. The photons that paint the world around you come from electrons shifting within atoms, or from heat radiating outward, or from stars burning far away. Each one carries its own energy, its own hue, its own message. When they arrive, your eyes read those messages without a single conscious effort. You're constantly decoding the universe without realizing it, interpreting the quiet language of energy. And so, when you look at the world, you can think of every colour as a signature, a unique imprint of energy carried by a photon on its journey through space. Reds whisper of warmth and low energy. Blues speak of higher energies and sharper transitions. Greens arise from the delicate balance of photons reflected by the living world. Even the colours you cannot see, the infrared warmth of a quiet room or the ultraviolet glow hidden in sunlight, play their part in shaping your surroundings. Colour is more than light. It is the universe communicating through energy. It is physics expressed as sensation. It is the soft translation of quantum behaviour into something gentle, vivid, and beautifully human. When you first hear that photons behave like both waves and particles, it can sound like someone is trying to have two completely different ideas at the same time. A wave is something that spreads, soft and continuous. A particle is something small and concentrated, arriving in one place at one moment. How could a single thing possibly behave as both? It feels like being told that a whisper can also be a pebble, or that a ripple on a pond can also be a droplet thrown into the air. But in the quiet world of quantum physics, this dual behavior is not a contradiction. It is simply the way nature expresses itself at its smallest scales. One of the gentlest ways to approach this idea is to remember that the universe does not owe us simplicity. It does not build itself according to what feels intuitive. The way things behave on everyday scales, balls bouncing, water flowing, shadows forming, does not necessarily reflect how nature behaves at the level of its most fundamental ingredients. The quantum world has its own rules, shaped not by intuition, but by the delicate structure of reality. And photons, being among the simplest quanta of all, reveal those rules with remarkable clarity. It helps to begin with the wave-like side of a photon. When a photon travels, it does not move like a tiny bullet fired from a microscopic slingshot. Instead, it spreads out. It moves as a gentle disturbance in the electromagnetic field, occupying a region of space rather than a single pinpoint location. You can imagine it as a soft ripple expanding on the surface of a perfectly still pond. The ripple is present across a wide area, yet it remains one ripple. It does not split into fragments just because it stretches across space. The photon is similar, one entity, existing in a way that feels more like a wave than a bead. Because of this wave-like character, photons can interfere with themselves. If you send light through two narrow slits and watch how it spreads on the other side, you see a pattern of bright and dark stripes. It looks exactly like the kind of interference you get when overlapping ripples on a pond strengthen one another in some places and cancel each other in others. The strange part is that this happens even if you send the photons through one at a time. Each single photon seems to behave as if it passes through both slits simultaneously, interfering with itself in a way that defies everyday logic, yet follows the rules of quantum physics perfectly. But despite this smooth, ripple-like behavior, photons also behave as particles. When they are absorbed, they deliver their energy in one clear, concentrated package. A photon never arrives halfway. It does not spread its energy out gently over an area. It arrives all at once, like a tiny tap on a sensor in your eye, or a small packet of warmth landing on your skin. Even if the photon had been spread across a wide region of space moments before, the instant it is detected in one location. The entire ripple collapses into a single, definite absorption event. This duality, spreading like a wave, arriving like a particle, is not something scientists invented to confuse anyone. It is something they discovered when they finally learned to look closely enough. Light sometimes behaves in ways that only waves should behave, and at other times it behaves exactly like something small and indivisible. This is not because light switches personalities or cannot decide what it wants to be. It is because the concepts of wave and particle, born from everyday experience, are simply not adequate to describe something as fundamental as a photon. A photon is neither a wave nor a particle in the classical sense. It is something more delicate, something that shares qualities with both while belonging entirely to neither. To keep this idea gentle, you might imagine a piece of music drifting through a room. The sound fills the space, spreading out like a wave. You can hear it from many places at once. Yet the energy that reaches your ears arrives in tiny bursts, activating the cells in your inner ear one packet at a time. The music behaves like a wave in one sense, and like individual pulses in another. It is not a perfect analogy, but it captures the feeling of something that is both spread out and discrete at the same time. Another soft metaphor is to picture a cloud drifting across a calm sky. The cloud has no firm edges. It spreads, stretches, and shifts. But if a raindrop forms within that cloud and falls, the raindrop is a single concentrated event. The cloud-like behavior before the raindrop forms and the particle-like behavior of the raindrop once it appears are connected, even though they seem so different. In the same way, a photon can spread like a cloud and arrive like a raindrop, without the two behaviors ever being in conflict. In quantum physics, this dual nature is entirely natural. Everything at the smallest scales behaves this way, not just photons. Electrons, atoms, and even molecules can spread out like waves, and then arrive in single, discrete moments. The universe seems to speak a quiet, consistent language at those scales, even if that language feels foreign to human intuition. What makes photons particularly magical is that their wave-like and particle-like behaviors are so easy to demonstrate. Shine light through a narrow gap, and you see diffraction, waves spreading out. Shine light onto a metal surface and measure the energy it gives off, and you see discrete particles delivering their energy in fixed amounts. You can view photons from either perspective, and both perspectives reveal something true about their nature. The key is understanding that the word wave describes how a photon travels, while the word particle describes how a photon interacts. These are not competing descriptions, they are complementary ones. The wave behavior tells you how the photon moves through space, spreading, interfering, forming patterns. The particle behavior tells you how the photon gives its energy to matter, always in one complete unit, never in fractions. If you imagine walking through a soft mist, you feel enveloped by something that has no clear boundaries. Yet when a single drop of dew lands on your hand, it arrives as one distinct droplet. The mist and the droplet are connected, part of the same phenomenon, just experienced differently. A photon shares this dual quality. The spreading is real. The single delivery is real. Both are expressions of the same underlying behavior. The soothing part of all this is that there is no expectation for it to feel intuitive. Even the scientists who discovered these behaviors were deeply puzzled at first. But over time, they learned to accept that nature is allowed to be subtler than our everyday experiences suggest. The quantum world does not need to mimic the classical world. It simply needs to be consistent with itself, and it is. So when you picture a photon moving through space, let it be a ripple, calm, expanding, elegant. And when you imagine that same photon being absorbed, let it be a tiny, perfect tap of energy arriving in a single moment. Both images are correct. Both are true. Both are part of the gentle mystery of light. The wave-particle puzzle, when viewed slowly and without strain, becomes less of a riddle and more of an invitation. It asks you to loosen your intuition, to allow nature to behave in ways that are more fluid and delicate than the solid world you know. It encourages a kind of calm openness, a willingness to hold two ideas together without forcing them into a single, simplistic shape. Light can spread like a wave. Light can arrive like a particle. And in that duality lies one of the most beautiful truths in physics, that the universe, at its smallest scales, is far softer, stranger, and more graceful than the everyday world would ever let you guess. When you picture a photon, it can be tempting to imagine it as a tiny bead or a miniature fleck of glowing dust drifting through space. something small, self-contained and tidy. But a photon is not a compact little object with a neat outline. It is something far softer and less confined. It is a disturbance in a field, and that disturbance can spread out over a surprisingly wide region while still remaining a single, indivisible quantum of light. This idea can feel almost contradictory at first. How can something spread out and still count as one thing? How can it be present in many places at once, yet always arrive whole? To make sense of it, imagine a quiet room with a candle burning in one corner. The smell of the candle slowly fills the air. It does not stay in one spot. It drifts, spreading through the room in a gentle, invisible cloud. Yet even though the scent has spread, it does not break into little pieces with separate identities. It remains a single presence, permeating the space softly and continuously. A photon behaves in a somewhat analogous way. When it travels, it does not remain confined to a single, pinpoint location. Instead, it spreads out, becoming a kind of shimmering possibility that extends through a region of space. It is not that the photon splits into parts or divides itself across space like a handful of sand scattered on the ground. It is that its presence becomes distributed. It is a pattern, not a particle in the everyday sense. It is a gentle cloud of probability, a shimmering suggestion of where it might be detected. This is where probability comes into the picture, though not in a mathematical way that demands symbols or equations. Think of it instead as a kind of soft anticipation. This spread of a photon is not a physical smear but a story of possibilities, each point in space carrying its own quiet chance of being the place where the photon reveals itself. The wider the spread, the more locations are included in this story. Yet the photon itself is still one entity, not a collection of smaller ones. It may help to imagine a gentle fog rolling across a field at dawn. You might say the fog is everywhere in that space, but you would still think of it as one fog, not many. A photon, too, can extend across space without multiplying into separate pieces. It remains singular, even in its spread. And then comes the intriguing part. When a photon finally interacts with something, your eye, a leaf, a mirror, it arrives as a whole. It does not deliver half its energy here and half somewhere else. It does not tap 3 senses in your eye and declare the job done. Instead, it collapses all of its possibilities into one definite event, one place, one moment, one complete transfer of energy. The way it spreads out is not a division. It is a kind of quiet searching. It is the universe offering a range of potential locations for the photon to complete its journey. And when the moment finally arrives, when the photon is absorbed, when its energy slips into the atom or the molecule waiting to receive it, all of that spread collapses down to a single point. Not because the photon has snapped back together, but because the act of absorption completes the story. Imagine receiving a letter that could have been delivered to any number of addresses. For days it might drift through a postal network, its ultimate destination not yet decided. But when it reaches your mailbox, it arrives as one whole letter, not fragments scattered across several houses. Its journey may have been uncertain, but its arrival is definite. The photon works in a similar way. It travels in a state of possibilities, but it lands as a singular event. This behavior can feel mysterious, especially because nothing in your daily experience spreads and collapses in the same way. A cup of water does not spread across a table and then leap into a single droplet. A piece of fruit does not scatter into vapor and then reappear whole somewhere else. But photons, being fundamental quanta of energy, live in a world where presence is fluid and detection is exact. If you want a softer picture, imagine throwing a pebble into a perfectly calm lake. The ripples that form spread outward gracefully. They do not break into separate bodies of water. They are one pattern stretching across the surface. Now imagine that this ripple travels across the entire lake. When it finally reaches the far shore, it delivers all its energy in a single moment, a tap, a soft arrival, before fading entirely. This is how a photon spreads and arrives. The ripple carries the possibility of interaction across a wide space, but the actual event occurs in one specific place. This is why photons can interfere with themselves in experiments, yet always deliver their energy in a single whole quantum when detected. They can act as waves during their journey, and as discrete particles when they meet an object capable of absorbing them. These are not contradictory behaviors. They are simply two expressions of the same underlying nature. You can think of the wave-like behavior as an unfolding, a poetic exploration of space. The photon stretches out, touching many places in a gentle, probabilistic way. But the particle-like behavior is the conclusion. It is the moment the photon gives up its energy, ending its existence as light, and beginning its influence in some other form, perhaps as warmth, perhaps as a chemical reaction, perhaps as a tiny electrical signal in your eye. The photon's ability to spread and remain whole at the same time reveals something profound about the quantum world. On this level, reality is not made of little objects flying around like tiny marbles. It is made of events, of possibilities, of patterns in fields that arise and vanish with seamless grace. A photon is not a miniature bead travelling in a straight line. It is a story written in probabilities, one that unfolds across space until the final sentence is written in a single place. This may feel abstract, but it is also beautifully serene. There is no chaos in a photon spread, no frantic scattering, no confusion, just a quiet expansion and an equally quiet conclusion. Everything about it follows the natural rhythm of the field it inhabits. The next time you see light reflecting off a window or shining softly through a curtain, you can picture the photons arriving not as tiny pellets, but as delicate ripples completing their long journey. They have spread across space, searched the landscape of possibilities, and finally found their moment of interaction. They arrive whole because that is the only way they ever exist, as complete quanta of energy, born in motion, travelling in patterns and ending their story in a single gentle touch. In this way, a photon spread is not a contradiction. It is a quiet demonstration of nature's ability to be fluid and definite at the same time. A photon can reach across a room and yet appear in a single point. It can be many possibilities and yet one event. It can be a ripple and a particle, a presence and a moment, all without ever being made of parts, all while staying whole. When a photon begins its journey, it is simply a tiny pulse of energy, drifting through the electromagnetic field, gliding forward with no weight and no hesitation. But eventually, almost inevitably, it will meet matter. It might brush against a leaf, slip into your eye, bounce from the surface of a lake, or sink into the dark fibres of a carpet. And what happens in that moment, when this massless, delicate ripple meets the solid world, reveals some of the strangest and most beautiful behaviour in physics. One of the simplest things that can happen is absorption. When a photon reaches an atom or a molecule and its energy matches just the right amount that an electron inside can accept, the photon disappears and its energy becomes part of that atom. It is a quiet handoff, like passing a note from one person to another. The photon does not bounce or split. It simply ends its existence as light and begins a new chapter as energy inside matter. This is how your skin warms in sunlight, how plants power photosynthesis, and how your eyes sense even the faintest glimmer. Absorption is a gentle exchange, seamless and final. Another possibility is emission, the reverse of absorption. When an electron in an atom relaxes to a lower energy level, it releases the extra energy it no longer needs. That release forms a new photon. You can imagine this as a tiny sigh of energy leaving the atom, drifting away as a pulse of light. The universe is full of these quiet releases, inside stars, inside glowing embers, inside fireflies. Photons are constantly being created and absorbed everywhere, a steady cycle of energy moving through the world. Reflection, however, introduces a different kind of interaction. When a photon approaches a reflective surface, like a calm lake or a polished piece of metal, it can be bounced away. But even this bouncing is not the solid, mechanical rebound of two objects hitting each other. The photon is absorbed and then re-emitted by the electrons in the surface almost instantly, sent off in a new direction. To the photon, the change in direction feels smooth and immediate. To you it looks like a crisp reflection. A mirror is nothing more than a surface where many atoms work together to return photons in a coherent, orderly way, letting you see your face in polished glass, or watch the sky shimmer on the surface of water. Refraction, light bending as it travels through materials like glass or water, adds another layer of quiet complexity. When light enters a new material, its path changes. Not because the photon slows down in the sense of a car pushing through mud, but because the pattern of absorption and re-emission inside the material nudges the photon's direction. Imagine walking through a crowd where people guide you slightly left or right without stopping you. You still move forward, but your path shifts gently in response to their subtle cues. A photon entering glass experiences a similar collective influence from the electrons inside the material. The path bends gracefully, giving rise to lenses, rainbows, and the way a straw in a glass of water appears bent. There is nothing abrupt about it. It is a gentle steering, almost like a whispered suggestion guiding the photon's way. Transparency, which can feel like a magical property, emerges from the same behavior. A material is transparent when its electrons do not prefer to absorb the energy carried by visible photons. If the energy of the incoming photon does not match any of the electron transitions available, the photon passes through instead of being absorbed. It becomes like a guest who arrives at a party where no one is expecting them. The atoms quietly let them slip through without interruption. This is why clear glass, water, and certain crystals allow light to pass almost untouched. Their electrons are simply not interested in the energy that visible photons bring. On the other hand, materials that appear opaque do absorb visible light. Their electrons readily take in the photon's energy or scatter it in many directions, preventing it from passing through. When you look at a wooden table, a wall, or your own hand, you're seeing materials whose electrons welcome the energy of the photons that arrive. They absorb some of the light and reflect or scatter the rest in ways that create the colors and textures you see. Scattering in particular is one of the most enchanting ways photons meet matter. You can picture scattering as a gentle nudge that changes the photon's direction. This nudge can happen in air molecules, water droplets, dust, or the faint particles floating in a sunbeam. When light encounters these tiny particles, it is deflected and sent off on a new path. Some photons scatter more easily than others. Shorter wavelength light, the kind that appears blue to your eyes, scatters more readily in the atmosphere, which is why the daytime sky glows with such a soft, expansive blue. At sunset, when the sunlight travels through more of the atmosphere, the blue and green photons are scattered away before reaching you, leaving behind the longer, warmer wavelengths. That is why the setting sun paints the horizon in shades of red and gold. Even the whiteness of clouds is a story of countless scatterings. Clouds are made of droplets large enough to scatter all wavelengths of visible light fairly evenly. The result is a gentle blending of colours that appears white to your eyes, like a soft blanket stretched across the sky. Then there are materials that shimmer or sparkle, because they scatter light in different directions. Rough surfaces, powdered chalk, beach sand, all reflect light in a somewhat chaotic pattern, causing them to appear matte or softly bright. The light that reaches your eyes from these materials is the result of photons being nudged again and again, softly redirected until they find their way to you. What makes all these interactions so strange and beautiful is that the photon is not a tiny object being pushed around. It is a disturbance in a field, responding to the structure of matter in ways that are delicate and precise. Every reflection, every refraction, every scattering is a conversation between the photon and the electrons in the material, a quiet negotiation that determines the photon's fate. This gentle negotiation is happening constantly around you. When you look at a cup of tea, photons reflect from its surface to reveal its shape. When you gaze through a window, photons pass through because the glass allows them to. When you shield your eyes from bright light, you are blocking photons that would otherwise be absorbed by your retina and translated into electrical signals, giving you the sense of vision. Every moment you spend seeing, feeling warmth, or moving through the world is shaped by these quiet interactions. It is soothing to realize that nothing chaotic is happening underneath these everyday experiences. There is no frantic battle between photons and matter. Instead, there is a soft choreography of absorption and release, of gentle nudges and graceful redirections. Photons meet matter in ways that are elegant, predictable, and full of subtlety. And so, the next time sunlight filters softly through curtains or dances over the surface of a river, you can imagine the countless photons involved, some being absorbed, some passing through, some scattering like tiny wanderers nudged off course. Each one is part of a calm, intricate dialogue between energy and matter. Each one is a reminder of how quietly and beautifully the universe works, even in its smallest details. The moment a photon reaches your eyes, an extraordinary sequence of events begins, one so quiet, so delicate, and yet so central to your experience of the world that it almost feels miraculous. Light drifts across space with no mass and no intention, but once a photon meets the surface of your eye, everything changes. That tiny pulse of energy begins a chain reaction that ultimately becomes sight, colour, shape, and meaning. To understand how you see a photon, imagine first the entrance of your eye. Light slips through the clear surface, glides through the lens, and settles onto the thin light-sensitive sheet at the back, known as the retina. The retina is an extraordinary structure, packed with millions of cells designed to respond to light. These cells wait patiently in the darkness inside your eye, alert for the arrival of even a single photon. Your eyes contain two types of light-detecting cells, rods and cones. Cones are responsible for colour vision. They allow you to see reds, greens and blues, and they work best in bright daylight. They are the artists of your vision, interpreting the world in rich, vivid hues. Rods, however, are the quiet night watchers. They cannot distinguish colour, but they are astonishingly sensitive. In very dark conditions, rods can respond to single photons. One tiny pulse of light, born perhaps millions of years ago in the heart of a distant star, can slip into your eye, strike a rod cell, and be detected. When a photon reaches one of these cells, it is absorbed by a molecule tucked neatly inside. That molecule changes shape in response to the photon's energy, like a lock turning when the right key is used. This shape change triggers a cascade of chemical reactions, tiny signals that flow from molecule to molecule until they reach the base of the cell. There, the chemical changes are converted into an electrical impulse. The photon, which began its life as a ripple in the electromagnetic field, has now become a message. This electrical signal travels along a network of interconnected cells within the retina. Each cell refines the message slightly, enhancing edges, adjusting contrasts, quieting noise. Only after this careful processing does the signal begin its journey along the optic nerve toward the brain. What is remarkable is that you never notice any of this. You're not aware of the photons striking your retina or the chemical reactions unfolding. All you know is that you can see. When the signal finally reaches the visual cortex at the back of your brain, an entirely new transformation begins. The brain does not simply play back an image the way a camera displays a photograph. Instead, it interprets. It guesses, it fills in details, it makes decisions about what matters and what does not. Much of what you believe you see is a combination of actual signals from photons and the brain's best guesses about what should be there. Occasionally the brain guesses incorrectly, which is how optical illusions manage to fool it. In a way, the brain is like an overly enthusiastic storyteller, very good at filling in gaps, occasionally creative in ways you did not ask for, and rarely interested in admitting uncertainty. This guessing is not a flaw, it is part of what makes vision so rich. When light is scarce, or when objects move quickly, or when the world presents only fragments of information, the brain uses memory and context to complete the picture. You might see a shadow and recognize it as a familiar object before you consciously analyze it. You might glimpse movement out of the corner of your eye and know instantly that someone is approaching. All of this interpretation begins with the simple act of absorbing photons. What makes this even more beautiful is that your eyes are not passive windows. They constantly adjust, modifying their sensitivity to match the world around you. In bright sunlight, your pupils shrink to protect the retina. In darkness, they widen, inviting more photons in. The rods become more active, ready to detect even the faintest glimmer. This dynamic adjustment allows you to experience everything from the brightness of midday to the soft glow of starlight. In both extremes, photons guide your perception. Consider for a moment how light interacts with your surroundings before reaching your eyes. It bounces from walls, from leaves, from water, from the surfaces of everyday objects. Each surface reflects, absorbs, or scatters photons in its own way. When you look at a red apple, what you actually see are the photons the apple did not absorb. Those photons reach your eye carrying the precise energy that your cone cells interpret as red. Your brain then constructs the idea of the apple, its shape, texture, depth, and color from these incoming signals. The apple itself never sends you a picture. It simply redirects photons, and you assemble the rest. This interplay of light and perception happens constantly, even when you are unaware of it. When you close your eyes, the visual world does not vanish completely. There may be faint flashes or drifting shapes. These are signals from cells inside the retina firing randomly or responding to internal changes. The brain, ever eager to explain things, sometimes interprets these signals as patterns. It does this because it prefers a story to silence. Even in darkness, your neurons murmur among themselves, keeping the machinery of sight ready for the next photon. It is also worth remembering that all the scenes you experience, the colours of sunrise, the glow of city lights, the shimmer of waves, the quiet pale of a winter morning, are shaped by photons that began their journeys far from you. Some come from the sun, crossing nearly 100 million miles before reaching Earth. Others originate in lamps, screens, candles, or reflections bouncing from nearby surfaces. From every direction, light arrives, and your eyes patiently translate it into vision. There is a soft humility in the way your eyes work. They do not demand powerful beams of light or dramatic displays. They can begin with a single photon, one quantum of energy, one tiny ripple in the electromagnetic field. That is enough to start the cascade that leads to perception, enough to let you detect the faintest star in the night sky or the smallest movement beside you. Vision becomes even more remarkable when you remember that the world you see is not a perfect reproduction of reality. It is a carefully crafted interpretation. The brain emphasizes some details and ignores others. It blends information from both eyes to create depth. It relies on experience to recognize shapes. At times, it invents patterns that are not really there. But at the heart of this interpretation, anchoring it firmly to the outside world, are photons. They are the messengers that deliver the raw material of sight. So the next time you open your eyes and take in the quiet details of your surroundings, you can imagine the invisible journey unfolding. Photons drifting through the electromagnetic field. Cells waiting patiently in the retina. Molecules changing shape. Electrical signals racing along nerves. And the brain weaving all of it into a coherent, meaningful world. In that sense, every moment of vision is a partnership between light and the mind, a dialogue between the outside and the inside, a gentle collaboration that begins with a single photon. Imagine, just for a moment, drifting into a dream where you can slip into the path of a photon. Not becoming the photon, of course, because a photon is far too simple for that. No mass, no parts, nothing for you to merge with. But imagine floating beside it, travelling alongside its motion the way you might walk beside a friend on a quiet evening. You're not the photon, but you are close enough to sense its world, close enough to let your imagination rest in its rhythm. A photon is born in motion. The instant it comes into existence, it moves at the speed of light. There is no pause, no moment of hesitation, no gentle acceleration, as if it is deciding how fast to go. Its entire existence is a journey outward. And so, when you drift into this imagining, you find yourself moving with it at a pace that no object with mass could ever achieve. There is no wind, no friction, no sense of rushing. Instead, there is a kind of perfect stillness wrapped around perfect motion, a paradox that feels strangely peaceful. From this vantage point, time behaves differently, not in a dramatic science fiction kind of way, but in the quiet, profound sense that the familiar rules of clocks and seconds no longer apply. When something with mass travels close to the speed of light, time slows for it relative to the world around it. The closer it gets, the more time stretches out. If it could ever reach the speed of light, time would stop entirely. For a photon, which travels exactly at that speed, time does not pass at all. Its entire existence, from the moment it is created to the moment it is absorbed, happens without duration from its own perspective. This does not mean a photon is conscious or aware. It does not possess a viewpoint or a sense of passage. But in your gentle imagining, this timelessness becomes a kind of meditation. You can picture yourself floating beside a photon as it leaves the surface of the sun. To the photon, nothing separates its beginning from its end. The journey that takes 8 minutes from the perspective of Earth or millions of years for photons released deep inside a star's core, would feel like a single moment, a single breath, if a photon could feel at all. To you, drifting alongside it in this mental picture, the journey feels both instantaneous and beautifully extended. You can imagine the sun shrinking behind you, the space between planets sweeping past, the darkness expanding in every direction. But at the same time, you feel no sense of acceleration or strain. The universe slides around you without resistance. It is like gliding across a perfectly smooth sea, where the distance between waves unfolds effortlessly. As you travel farther, something curious happens. The distances between stars, which seem vast and almost unimaginable, when seen from a stationary point, begin to feel softer and more connected. The light years between suns compress in perception, because you are moving at the cosmic speed limit. The separation between places turns into something that feels less like miles and more like a gentle flow of scenery. You might picture drifting past the orbit of Jupiter, then Saturn, then leaving the familiar space of the solar system entirely. The warmth of the sun fades behind you, becoming a distant glow. Ahead lies the deep quiet of interstellar space, where stars shine like scattered embers. This darkness is not empty. It is rich with invisible fields, with drifting dust, with particles and forces that fill the universe, even when you cannot see them. As you glide through this cosmic quiet, you sense how the rules around you differ from the rules you know. In ordinary life, distance is something you cross by moving from one place to another over time. But here, alongside a photon, time has slipped away. The journey itself becomes a kind of single moment stretched out like a dream. There is movement, but no ticking. Travel, but no waiting. You might find yourself approaching a distant star. The light from that star flows outward in all directions, just as the light from your starting point once did. The space around you feels woven with ripples of energy, some soft and gentle, others sharp and bright. You drift through them effortlessly, sensing their presence without disturbance. There are other photons on their own journeys, each one carrying energy from one corner of the universe to another. If you continue drifting in this imaginative state, you may find the distance between galaxies folding into something like a quiet path. The Milky Way transforms from an immense spiral to a graceful swirl beneath you. Another galaxy appears like a ghostly island, floating in a sea of dark. Yet through all this vastness, your sense of motion remains peaceful. There is no sense of rushing. The speed does not feel fast. It simply feels like the natural state of this strange, massless companion you're following. Now imagine approaching the end of the journey, wherever that may be. Perhaps the photon is heading toward the leaf of a plant, or the sensor of a telescope, or the surface of a distant world. When the photon is absorbed, when it gives its energy to an atom waiting patiently to receive it, the journey ends in an instant. For the photon, that ending is the whole story. No beginning, no middle, no travel. Just creation and absorption linked together, separated only by the world's experience of time. From your viewpoint in this dreamlike imagining, the arrival feels gentle. The light touches matter, energy is transferred, the ripple in the electromagnetic field settles, and the photon ceases to exist. There is no drama in its ending, no lingering echo, just a quiet completion of the path it began. Riding alongside a photon, even only in imagination, becomes a meditation on motion and stillness, on time and timelessness, on the strange elegance of the universe at its smallest scales. It invites you to feel the rhythm of light not as speed, but as flow, not as distance, but as connection, not as a race from one point to another, but as a single, seamless moment stretched across space. And when you return from this reverie to the everyday world, the light around you may feel a little different, softer perhaps, more mysterious. Each photon drifting into your eyes, each glint on a surface, each shimmer in a shadow carries a story that, from the photon's own strange existence, unfolds in no time at all. It is a reminder that the universe contains ways of being that do not match your intuition, yet remain profoundly beautiful. And sometimes, letting your imagination drift beside a photon is enough to appreciate just how gentle, strange, and wondrous that beauty really is. Every living thing you know, every plant, every animal, every cell in your body is part of a long chain of chemistry. Molecules meet, bonds form, bonds break, energy moves from one place to another. Life is, in a very deep sense, a continuous dance of chemical reactions. And while many of these reactions are gentle enough to happen in the dark, the grand story of life on Earth depends on something far more luminous. Photons, drifting outward from the sun, provide the energy that drives the chemistry of life. Without them, the world would be cold, still, and silent. To understand why photons make chemistry possible, imagine the molecules inside a leaf on a bright morning. These molecules sit in a delicate structure designed by evolution to catch light. When a photon arrives after crossing nearly 100 million miles of space, it does not crash into the leaf like a tiny stone. Instead, it is absorbed by a molecule crafted for the task. This molecule, often chlorophyll, holds an electron poised at just the right energy level. The photon meets it, gives up its energy, and the electron jumps. That single jump begins the vast chemical machinery of photosynthesis. This might sound simple, but it is anything but. Photosynthesis is one of the most intricate chemical symphonies on the planet. A single photon provides just enough energy to push an electron into an excited state. And once it is there, the plant uses that energy to separate charges, move electrons along pathways, and eventually build sugars out of carbon dioxide and water. Every leaf is a quiet factory powered by photons. The sunlight drifting gently across fields is not just illumination. It is the fuel that makes forests breathe and oceans bloom. On a molecular level, photons are perfectly suited for this role because they carry discrete amounts of energy. Not too large, not too small, but precise packets that can shift electrons in predictable ways. When an electron in a molecule jumps to a higher energy state, that molecule becomes reactive. It can break old bonds, form new ones, or pass its energy along to another molecule. Photons essentially unlock the potential for chemical change. They provide the kick that allows molecules to rearrange themselves in creative, life-sustaining patterns. Plants use photons to build the sugars that feed the entire food chain. Without photons, there would be no trees, no grasses, no flowers, no fruits. And because nearly every animal depends indirectly or directly on plants, there would be no birds, no mammals, no insects, and no humans. Life on Earth is, quite literally, sunlight arranged into living shapes. But plants are not the only organisms that rely on photons. Even in humans, photons play roles in chemistry. Sunlight helps your skin produce vitamin D, a molecule essential for bones and immune function. Light influences your sleep cycles and mood through chemical pathways inside the brain. The photons entering your eyes trigger reactions that allow you to see. In all these cases, light initiates chemical change, sometimes subtly, sometimes profoundly. At the heart of these changes lies a simple truth. Chemistry is governed by the movement of electrons. Molecules are built from atoms, and the atoms hold on to electrons in patterns of bonds and shapes. To change a molecule, you often need to move its electrons into a new configuration. Photons are masters at this. Their energy is exactly the right size to lift an electron from one state to another, setting off a cascade of reactions. If the energy is too low, nothing happens. If it is too high, the molecule may be damaged. But visible light carries precisely the amount of energy needed to drive complex chemistry without tearing molecules apart. It is almost as if life evolved to tune itself to the energy of sunlight, finding just the right balance between usefulness and safety. When ultraviolet photons arrive with too much energy, they can break DNA, but visible photons are gentle enough to work with. They warm, they energize, but they do not harm. They strike the perfect middle ground. The chemistry of vision is another beautiful example of photons at work. When a photon enters your eye and strikes a molecule in a photoreceptor cell, that molecule changes shape. This tiny twist, caused by the photon's energy, triggers a chain reaction that ultimately produces the electrical signals your brain interprets as sight. Every color you see begins as a molecule changing shape because of a single photon. The world you perceive is built from countless such reactions, each one set in motion by a tiny pulse of light. In a sense, photons act as messengers between the physical world and the chemical world. They carry information about the environment, its colors, its warmth, its brightness, and deliver that information through chemical changes. A photon striking your skin tells your body about sunlight. A photon absorbed by a leaf informs the plant about energy availability. A photon reaching the depths of the ocean can be detected by creatures adapted to the faintest glow. Light is a universal communicator, speaking to molecules in a language they understand. The beauty of photon-driven chemistry is not just in how it powers life, but in how gentle and continuous it is. Photons slip into molecules softly. They do not push or shove. They do not tear or burn. They provide just enough energy to let chemistry unfold naturally. Life thrives not because light forces it to grow, but because light nudges it in just the right way. If you imagine a world without photons, the stillness is unsettling. Chemistry would continue in some forms, but slowly and without direction. Oceans would be dark and barren. Plants could not build their food. Animals would have nothing to eat. Even the earliest bacteria that once learned to capture photons billions of years ago would not have found their path. Photons gave life the energy it needed to flourish, to grow, to diversify, and eventually to become curious enough to ask where photons come from. Every breath you take contains oxygen created by photon-driven chemistry inside ancient oceans. Every meal you eat contains energy stored from sunlight captured long before you were born. Every moment you spend seeing the world is shaped by photons slipping into your eyes and rearranging molecules. Light is not just the background to life. It is the thread that weaves life together. When you look at the world illuminated before you, you are seeing chemistry in motion, powered by photons that began their journey in the heart of a star. The quiet glow of the morning, the colors of a forest, the warmth on your skin, the energy in your cells, all of it is the work of light entering matter and inviting it to change. In that sense, photons do not just make chemistry possible, they make life possible. They give molecules the spark they need to reach upward, to grow, to breathe, and to become part of something larger. Life is sunlight transformed, shaped by the gentle work of photons moving across space and into the heart of chemistry. When people hear the word vacuum, they often imagine a perfect emptiness, a silent void, a place where nothing exists, nothing moves, and nothing stirs. It sounds peaceful, almost like a cosmic meditation chamber. But in the language of modern physics, the vacuum is something far stranger and far livelier. It is not a blank canvas. It is a restless sea woven from the fabric of fields, a place where activity dances just beneath the threshold of what we normally see. To imagine the quantum vacuum, picture a perfectly still pond. At first it seems quiet, a smooth mirror reflecting the sky. But if you look closely, you notice subtle motions, tiny ripples forming and fading, delicate tremors that come and go without any visible cause. The water is never truly at rest. It quivers with possibilities. The quantum vacuum behaves in a similar way, although its ripples are not waves of water, but faint fluctuations in fields that fill all of space. Every point in the universe, no matter how far from stars or planets or drifting dust, is filled with these fields. And even when there are no particles present, the fields never settle completely. They tremble faintly, as if the universe itself cannot sit perfectly still. These tremors are called vacuum fluctuations, and they are the foundation for some of the most mysterious phenomena in physics. Within these fluctuations, pairs of particles and antiparticles can momentarily appear. They do not persist, and they do not travel. They are brief, fleeting disturbances, tiny borrowings of energy that are immediately returned. Among these ephemeral visitors are the so-called virtual photons. They're not photons in the familiar sense. They do not stream across space. They're not absorbed by your eyes or released by excited atoms. Instead, they appear as quiet, momentary stirrings of the electromagnetic field. To understand this without diving into mathematics, imagine a deep ocean at night. You cannot see what lies beneath the surface, but occasionally you notice a faint glimmer, a swirl of movement, a trace of something appearing and disappearing before you can fully identify it. The movement is real, yet not the same as the movement of waves you can touch with your hands. Virtual photons are like those faint glimmers beneath the surface. Short-lived, subtle, and impossible to separate from the darkness they rise from. These virtual photons are part of what gives the vacuum its energy. Despite being empty, the vacuum exerts gentle influences on the world. It can shift the energy levels inside atoms. It can alter the behavior of particles. It can even generate a soft pressure that pushes on objects placed very close together. All of these effects come from the underlying, ever-present activity in the fields that fill space. Perhaps the most remarkable thing is that even photons travelling through space are shaped by this restless background. A photon moving across the universe is not gliding through stillness, but through a sea of subtle fluctuations. These fluctuations are not obstacles or bumps, but they contribute to the landscape the photon travels through. The vacuum is not nothingness. It is the quiet stage on which the drama of particles unfolds, always humming with potential. And yet, for all this activity, the vacuum remains incredibly calm on the scales we normally experience. You do not see it or feel it when you walk across a room. You do not sense its subtle tremors when you sit in a quiet field. The fluctuations happen on scales so small and so fleeting that they slip beneath perception entirely. They are whispers beneath whispers, a quivering beneath stillness. The idea that the vacuum is alive with activity can feel unsettling at first. It seems to contradict the intuitive sense that emptiness should be truly empty. But once you sit with the idea for a while, it becomes strangely comforting. Even in the absence of everything, the universe continues to move. The fields remain present, ready to create particles, ready to react, ready to carry energy. The vacuum is not a void, it is a foundation. Virtual photons do not behave like normal photons, and they do not follow the same rules. They cannot be seen, detected, or captured. They flash into existence as part of the mathematical and physical structure of the electromagnetic field, helping to mediate forces between charged particles. They act like quiet messengers in the background, shaping interactions without ever becoming real travellers of light. You might imagine them as ghostly ripples that rise for an instant and then return to stillness, leaving behind only a trace of their influence. They have no journeys, no destinations, no stories in the sense that ordinary photons do. But without them, the electromagnetic force would not behave the way it does. Atoms would not bind together properly, chemistry would fall apart, the stability of matter would collapse. Virtual photons are the silent threads that hold many of the world's structures together. This can feel abstract, but a metaphor can help. Think of a violin string resting between two fixed points. Even when no one is touching it, the string holds a potential for vibration. The slightest breath of air, the softest disturbance can set it quivering with sound. The vacuum is similar. It holds the potential for particles. Even when no real particles are present, the fields that fill space are never fully motionless. They are ready to respond, ready to vibrate, ready to produce ripples when energy arrives. And sometimes those ripples become real photons. A photon might be born deep inside a star, where an excited atom gives up energy. Or it might arise from the warmth of a furnace, or from the glow of a lightning bolt, or even from a chemical reaction inside a firefly. Every time a real photon is created, it emerges from the underlying field, the same field that shivers with virtual photons in the vacuum. The difference is longevity. A real photon travels. It lives a journey. It can be absorbed, scattered, or detected. A virtual photon appears only as a brief tremor, a necessary part of the quiet machinery of forces. One is a traveller, the other is a flicker in the deep. Once you begin to see the vacuum not as empty, but as a restless sea of potential, the universe takes on a new kind of depth. Every photon you see, every sparkle of light, every warm glow, every reflection, is born from this quiet foundation. Even the darkness between stars is alive with activity too subtle to see, but essential to everything that exists. The quantum vacuum is mysterious, but not frightening. It is the silent background that supports all motion, all matter, all light. It is the stage upon which photons arise and fade. In the quiet rhythms of its invisible fluctuations, you can imagine the universe breathing, softly, endlessly, patiently, waiting for the next spark of energy to begin its journey. When photons move through the gentle spaces of everyday life, gliding through air, reflecting off water, warming your skin, their behavior feels calm and familiar. But the universe contains places where gravity bends space-time dramatically, where temperatures soar, where matter is crushed into unimaginable densities. And even in these extreme environments, photons continue their quiet journeys, shaped not by chaos but by the deep, graceful structure of the cosmos. To imagine how photons behave near a massive object like a star, picture space-time as a soft fabric. A star presses into this fabric, curving it the way a heavy sphere might curve a stretched sheet. When a photon passes through this curved space, it follows the bend naturally, not because it is pulled like a pebble tossed toward a well, but because the very geometry it moves through has changed. Light always travels along the straightest possible path through space-time, but near a massive object, straight lines themselves curve. This creates effects that are both subtle and poetic. For instance, when a photon climbs away from a strong gravitational field, say, leaving the surface of a dense star, it loses a little energy along the way. Not enough to slow down, because photons never slow, but enough to stretch the light toward the red end of the spectrum. This stretching is called gravitational redshift. You can imagine it as the photon making a gentle upward climb, giving up a touch of its energy to escape the star's influence. The light grows slightly redder, as though the star has whispered a quiet farewell, releasing its grip little by little. From a calm, distant perspective, this redshift is almost like watching a swimmer rise from the deep ocean toward the surface. The deeper they begin, the harder they must work to reach the open air. A photon beginning its journey near a massive star does not struggle, but it emerges changed. Its energy reflects the depth from which it came. Black holes take this idea to an astonishing extreme. Their gravitational pull is so intense that even the geometry of space-time becomes dramatically curved. If you imagine a photon wandering close to the edge of a black hole, without crossing the boundary known as the event horizon, it can find its path bent into gentle arcs or dramatic loops. In some situations, a photon can even circle the black hole, held in a precarious orbit where space curves just enough to keep it looping endlessly. This region, sometimes called the photon sphere, is like a cosmic roundabout where light can circle without ever escaping or falling in, provided it moves at precisely the right angle. But if a photon drifts too close, crossing the event horizon, its journey ends in a way that defies everyday imagining. Inside that boundary, every possible path leads inward. The photon cannot escape because space-time itself funnels everything toward the center. The photon does not slow or struggle. It simply follows the shape of the universe in that region. From the outside, its light becomes stretched to redder and redder wavelengths until it fades beyond detection, as though the black hole gently erases its final whisper. Despite the intensity of these regions, the behavior of photons remains serene. They do not panic or twist or break. They follow the rules of space-time, flowing through its curves with the same grace they show in the emptiness between stars. Speaking of that emptiness, consider photons born in the early universe. These photons, which now form the cosmic microwave background, have been travelling for nearly the entire history of the cosmos. When they were created, the universe was unimaginably hot and dense, a glowing fog where photons were constantly scattered by particles. But as the universe expanded and cooled, photons were finally able to travel freely. Since then, they have been drifting through space for billions of years. As the universe expands, these ancient photons stretch in wavelength. Their colours shift from intense brilliant light to softer and softer tones until they settle into the faint microwave glow that now fills the cosmos. You can imagine their journey like the slow stretching of a ribbon as someone walks away holding one end. The ribbon becomes longer and thinner, but it never snaps. In the same way, the photons become gentler, cooler, softer as they move through the expanding universe. These early universe photons are some of the most peaceful travellers imaginable. They have crossed distances so immense that the human mind can barely grasp them, yet they continue onward, carrying the imprint of the cosmos's earliest moments. They whisper stories of what the universe was like long before galaxies formed, long before stars ignited, long before planets emerged. And yet these whispers are not fragile. They persist, steady and faint, like a soft hum beneath all of existence. Even in places of tremendous energy, photons move with composure. In the cores of stars, temperatures and pressures are so extreme that matter exists in states found nowhere else. Photons created there may take thousands of years to travel outward, constantly absorbed and re-emitted by atoms. The journey is slow, not because they move slowly, they always travel at light speed, but because matter redirects them endlessly. It is like trying to leave a crowded festival by walking through throngs of people who keep turning you around. The photon zigzags in a chaotic path until it finally escapes the star's surface and begins a direct, uninterrupted journey through space. Temperatures in these stellar cores can reach many millions of degrees, yet photons remain composed. They are not harmed by the heat. They do not burn or fade. They are simply created, redirected, and released. When they finally escape into open space, they glide forward with the same effortless grace as photons created by a candle flame or a lightning strike. Extreme environments do not change their essential nature. Photons near neutron stars experience even more extreme conditions. Neutron stars have gravity so intense and magnetic fields so strong that matter behaves in ways that defy intuition. Here, photons can be split into different polarization states or redirected in unusual ways. The magnetic field is so powerful that it can shape the path of light, guiding it along invisible lines. Yet even in these extraordinary surroundings, photons follow the same basic principles they obey everywhere else. They move through space-time, responding to its structure, and carrying energy with unwavering certainty. The universe is full of extremes, places of crushing gravity, blazing heat, unimaginable density or ancient expansion. And through all of it, photons persist as gentle travelers. Whether escaping a star's surface, circling a black hole, drifting through the quiet darkness between galaxies, or carrying the faint memory of the early cosmos, they remain elegant and consistent in their behavior. Perhaps the most soothing thought is that no matter how intense the environment, photons never lose their grace. They do not worry. They do not resist. They flow along the pathways carved by space-time itself, always at the same cosmic speed, always carrying their small packet of energy, always ready to share it with the next atom that meets them. In this way, photons become a thread that ties together the quiet places and the extreme ones. They are born in fire, shaped by gravity, stretched by the universe, and yet they remain unwavering messengers, gliding peacefully through the most dramatic regions of reality. Light seems so simple when you first look at it. It spills through a window and brightens a room. It reflects from a surface and reveals a familiar face. It glows from the stars and guides travelers across oceans. But when you look closely, really closely at the level of photons, light becomes a quiet doorway into some of the deepest truths about reality. Photons are small, but what they reveal is vast. Through their behavior, the universe hints at the nature of space and time, the subtlety of quantum events, and the mysterious connection between distant places. One of the first things photons teach us is that the universe is not static. Space is not a rigid backdrop on which events occur. It is flexible, stretchable, curved by mass and shaped by energy. Photons travel through space-time, and in doing so they trace its structure the way a droplet of dye reveals currents in water. When a photon curves around a massive star or is stretched by the expansion of the universe, it is not being pulled or tugged in the way objects with mass are. Instead, it is simply following the contours of reality as they are. The path of a photon is the universe drawing its own map. If space were perfectly flat and unchanging, photons would move in perfectly straight lines forever. But space bends, it expands, it whispers its secrets through the journeys of light. Every sunrise you see, every star in the sky, every reflection on water is shaped by the geometry of spacetime. Through photons, you're constantly reading these cosmic messages, even if you do not realize it. Photons also reveal something profound about time. Because they travel at the cosmic speed limit, they experience no passage of time themselves. A photon leaving a distant galaxy billions of years ago and arriving in your eye today experiences no delay. For that photon, the entire journey is a single instant. Time does not flow for light. It does not age, it simply moves. This says something extraordinary about the universe. Time is not universal. It is not the same for everything. It bends and stretches depending on how something moves through space-time. Photons show this in the clearest, calmest way possible. They glide through the cosmos without feeling any of the duration that shapes your days and nights. They show you that time is not a background rhythm, but a property of motion, a consequence of being made of matter. Light also reveals the strange behavior that lies at the heart of quantum mechanics. A photon can spread out like a wave, occupy a region of space, interfere with itself, and behave as though it travels down many paths at once. And yet, when it is detected, it arrives in one exact place, delivering one exact packet of energy. Its journey is written in probability, but its arrival is precise. This duality hints at something subtle about the world. Fundamental reality is not made of solid objects moving in predictable lines. It is made of possibilities, tendencies, and patterns in fields. Photons move through these landscapes of possibility with quiet certainty, showing you that the universe does not operate like a clockwork machine. It operates like a set of interconnected rhythms. Sometimes those rhythms feel wave-like. Sometimes they appear particle-like. Neither picture is complete, yet both are true. Perhaps one of the softest lessons photons teach is that connection can exist across incredible distances. When you see a star in the night sky, the photons entering your eyes may have travelled for years, centuries, or even millennia. They began their journey long before you were born, carrying with them the story of a place unimaginably far away. They crossed regions of space where no planets exist, where darkness stretches for trillions of miles, yet they found their way to you. In that moment, you're gently linked to something ancient and distant. Light makes the universe feel intimate. This connection shows you that the cosmos is not a collection of isolated islands. It is a network woven by the paths of photons, binding stars, galaxies, and observers together. Light is how the universe communicates, how it shares information about what is happening in one place, with everything else that can receive its message. Photons also speak quietly about uncertainty. They can never be pinned down in quite the way you pin down a pebble or a grain of sand. They spread out, drift, explore possibilities, and collapse only when you observe them. This behavior is not chaotic. It is precise, consistent, and deeply rooted in the structure of quantum fields. But it challenges the human instinct to see the world as solid and definite. Photons remind you that, at its core, reality is softer than it appears. Rather than being frightening, this softness can feel strangely comforting. The universe is not rigid, it is fluid, it breathes. Its smallest phenomena unfold gently, following laws that make room for possibility. Photons show you that reality is not a hard-edged sculpture. It is more like a musical composition, predictable in its rules, yet beautifully unpredictable in its expression. On a more personal level, photons reveal how much of your experience depends on interpretation. Everything you see is built from photons absorbed in your eyes and translated by your brain, and your brain does not simply record what arrives. It constructs meaning, it smooths edges, fills in gaps, and shapes perceptions. The world you perceive is partly created by photons and partly created by thought. In that partnership lies a hint that reality is not just external, it is also internal. Light provides information, your mind provides understanding. Even the colours you see are not properties of objects themselves, but interpretations of photon energies. A red apple looks red because of the photons it sends into your eyes, not because redness is an intrinsic feature of the apple. Photons teach you that colour, brightness, beauty and clarity exist in the space between the world and your perception of it. As you move through this reflection, the universe begins to feel both grand and intimate. Photons cross cosmic distances, yet their journeys end in moments that shape your sense of sight and warmth. They come from stars, but also from lamps and fireflies. They reveal the structure of space-time, but also illuminate the pages of a book. They act according to the laws of quantum fields, but also paint the everyday world with colour and shadow. Light connects the immense and the ordinary, the distant and the present, the cosmic and the familiar. Through photons, you can sense the scale of the universe without leaving your chair. You can glimpse the earliest moments of existence simply by listening to the faint glow of the cosmic background. You can understand how deeply intertwined things become when the smallest particle of light spans both the quantum world and the vastness of space. What photons tell you about reality, in the quietest voice imaginable, is that the universe is woven from relationships. Space relates to time. Fields relate to particles, energy relates to matter, and light relates everything to everything else. Reality is not a collection of separate things, it is a tapestry, and photons are the threads that run through the entire weave. And as these reflections gather softly, they guide you toward a deeper sense of closure. Light is not just something you see, it is something that reveals, something that connects, something that whispers truths about the world that would be hidden without it. Through photons, the universe shows you not only what it is made of, but also how delicately, how beautifully, and how surprisingly it all fits together. There is a quiet kind of beauty in realizing that photons, these tiny wanderers of the universe, are not made of anything at all. No smaller pieces hide inside them. No deeper structure waits to be uncovered. They are not built from parts the way atoms are, or stitched together like molecules, or assembled like the familiar object you hold in your hands. A photon is simply a pulse of the electromagnetic field, whole and complete, with nothing beneath it. And yet, this nothing is what shapes almost everything. It can feel strange at first to imagine something so influential having no internal machinery. You're used to thinking of complexity as something built from layers. A tree grows from cells. Cells contain molecules. Molecules contain atoms, and atoms contain smaller particles. But photons stand outside that pattern. They are fundamental. They do not emerge from deeper structures. They just are. And in this simplicity lies their elegance. Because they have no mass, they move effortlessly through the universe at the cosmic speed limit. Because they have no size in the usual sense, they can slip through spaces, interact with matter, and carry energy in the most delicate ways. Because they have no internal parts, they never decay or break apart. They are the purest carriers of information and energy that nature allows. This simplicity becomes even more remarkable when you look at how much photons accomplish. They warm planets, nourish forests, paint colours across the sky, and fill the world with visibility. They carry whispers from the earliest moments of the universe, still drifting across space after more than 13 billion years. They reveal the shape of galaxies, the motion of stars, the chemistry of distant worlds. They weave reality into something you can see, feel, and understand. All of that from a particle that is, in a sense, made of nothing. There is a softness in this thought, a reminder that not everything powerful is complicated. Sometimes the most foundational things are the most minimal. A photon carries no baggage. It has no hidden structure slowing it down or weighing it down. It is a single, indivisible note in the cosmic symphony, and yet without those notes, there would be no melody at all. When you look at the world illuminated around you, the gentle glow on a wall, the shimmer on water, the fading traces of sunset, it is all the work of these weightless, structureless pulses passing through space. They are everywhere, and they have been everywhere, shaping the universe with the lightest possible touch. And as this chapter settles into stillness, it becomes clear that the question, what are photons made of, leads to an unexpectedly poetic answer. They are made of nothing, yet they make everything visible. They carry no mass, yet they shape the warmth and colour of your world. They hold no structure, yet they reveal the structure of the universe. In their simplicity lies their wonder, in their emptiness lies their power, and in their brief, gentle journeys lies the light that lets you see. Light drifts through your life so quietly that it's easy to forget how extraordinary it is. Every moment you spend seeing, every warm patch of sunlight, every glimmer on a surface, every colour that settles into your memory comes from photons moving through the world. These tiny pulses of the electromagnetic field carry energy across unimaginable distances, yet they do so without mass, without parts, and without anything inside them at all. Across this exploration, the idea has remained beautifully simple. A photon is not constructed from smaller components. It holds no hidden gears, no internal workings, no layered structure waiting to be uncovered. It is a single, fundamental expression of the electromagnetic field complete in itself. And from this simplicity flows everything that light can do. Photons bring colour to the world. They make chemistry possible. They connect distant galaxies, pass through the vacuum, trace the curves of space-time, and allow you to sense your surroundings. They behave like waves spreading softly through space, yet arrive in single concentrated packets of energy. They reveal the rules of quantum mechanics while illuminating the pages of a book beside your bed. They travel from the hearts of stars to the surface of your eye, slipping gently into molecules that translate their energy into vision. They whisper stories about ancient galaxies, carrying messages that began their journey long before Earth existed. They drift through the early universe and still fill the night sky with a faint ancient glow. Light is both the smallest of things and the most expansive, touching the farthest edges of the cosmos and the quiet spaces of everyday life. There is something calming in recognizing how much arises from something so simple. Photons have no internal structure, yet they shape the world with subtlety and grace. They are weightless, yet they warm entire planets. They last for billions of years, yet they vanish the instant they are absorbed. They are both delicate and enduring, gentle and powerful, fleeting and essential. As this journey settles into stillness, you might feel a small sense of wonder at how light moves through your life, how it reveals the world without ever leaving a trace of itself behind. how something made of nothing can shape everything you see. And as you drift toward rest, it is comforting to know that even in darkness, photons are still on their way, traveling, reflecting, scattering, and waiting for the next quiet moment when they will meet your eyes.